Since this is a periodic motion, simple harmonic motion is something that repeats in a cycle over and over and over again. There's this term that's really important in these kind of repetitive motion ideas, and that's called the period. It's abbreviated with capital T, and it's a time. It's the time it takes to complete one complete cycle in any simple harmonic motion. So in our object here, this is what we're talking about. We're starting here at this maximum amplitude, and then the thing is going to move through one cycle like this. The amount of time it takes to go from the starting point back to the starting point through the whole cycle, that's the period. Well, our question that we are confronted with now is there some way to find the period of something that's in simple harmonic motion? In some physics books that are based on calculus, the approach will be completely different. It's actually simpler if you know how to do calculus, but we're assuming that nobody here knows this well enough to follow it probably, and so we're gonna do a trick. We're gonna make a little analogy that allows us to avoid using calculus. So the question is, can we find the period of something that's in simple harmonic motion? Now here's the trick. We're gonna imagine this little analogy. We're gonna imagine this. Here's a lamp. This lamp is, you can see these little lines here. Those are supposed to represent light waves. So there's light beaming down from this lamp onto this rotating disc, and this disc has got this pin here. So this red thing here, what that really is like a handle on a crank is what it is. So as the lamp shines down on there, it casts a shadow down here on the ground below. And as the thing spins around, of course, that shadow is going to move. And we're going to use this analogy to tie together what we know about rotating motion to simple harmonic motion. So the question is, as the shadow moves, is that shadow in simple harmonic motion? Because if it is, then we can use some stuff we know about circular motion to describe it more fully. So here's this drum with the handle way over on the right-hand side here, and it's going to start rotating this way. Watch what happens to this shadow. As the thing made two circles, we saw the shadow go back and forth, kind of like that mass on that spring. Was it really like that? Does that shadow make simple harmonic motion?
At this point, you have two options. If you're curious about does this shadow in fact really do simple harmonic motion, the rest of this video will explain that in detail and sort of prove to you that in fact the shadow does do simple harmonic motion. If just watching the picture of the shadow and the handle is enough to convince you that the shadow really is in simple harmonic motion, then you can stop this video here and then move on to simple harmonic motion C, part C, because that will pick up from after the proof that the shadow is in simple harmonic motion and take you through to the point where we know what the period is using what we know about circular motion. Your choice.
Let's try and figure it out. Well, let's take a close-up look at this and try and sketch some things out and make a little geometric sense out of this. Let's call the radius of this thing A. And let's say it's moved through some angle theta. The drum has rotated through some angle theta, the disc. And the shadow is now at position X down here. Well, that means this is also X, the distance from here to the pin. So what we're really doing is we're tracking the X position of that handle with respect to the radius, because that's where the shadow is going to be. When the handle is right straight above the center point, well, the shadow will be right below the center point. And so that's a good way of tracking where the shadow is. The shadow is at X. This vertical here we could call Y, but using Pythagorean theorem, we know what it really is. The dimension of this is really the square root of the hypotenuse, which is A squared, minus the other leg squared. So that's this length. So the sine of this angle theta, which is opposite over hypotenuse, is going to be equal to square root of A squared minus X squared over A. But A is really the square root of A squared, so here's another little trick. The sine of theta is square root of A squared minus X squared over the square root of A squared. Or you could say the sine of theta is equal to the square root of 1 minus X squared over a squared. Now, where have you seen that before? Well, where you've seen it before is when we were describing velocity of the block in the spring mass system. Maybe that's related to velocity. Let's take a look at the velocity of this pin. Sort of start this over. Starting here, let's take a look at velocities. Now, there are two things that have velocity here. One is the actual handle itself, and it's moving tangentially to the circle. So this is velocity of the pin, we're going to call it. And we have this velocity here, which is the velocity of the shadow. Now, if this is angle theta, then this angle right here is also theta. This is a right triangle here. If this is theta and tangent is perpendicular to the radius, then this is the complement of theta, 90 minus theta. So that makes this angle theta as well. Let's take this little triangle and blow it up. Here's what we've got. This is velocity of the pin. This is velocity of the shadow. And this angle right here is theta. So here's what this means. Opposite theta is Vs. Hypotenuse is Vp. So Vs over Vp is the sine of theta. Opposite over hypotenuse. But remember what sine of theta is? We just saw that the sine of theta, this same theta, is the square root of 1 minus x squared over a squared. So let's put these two together then. Vs over Vp is equal to the square root of 1 minus x squared over a squared. Here's what that means. Vs, the velocity of the shadow, is equal to the velocity of the pin times the square root of 1 minus x squared over a squared. Now this looks a lot like our equation that we had for the velocity at any point x in our spring mass system that we knew was in simple harmonic motion. That equation said this: the velocity was equal to the maximum velocity times the square root of 1 minus x squared over a squared. Is this really saying the equivalent thing? Well, it is, because the velocity of the shadow is equal to the velocity of the pin at its maximum size. And that's when that pin is right here. That's the fastest you'll ever see this shadow move. At that point, it's moving at exactly the same speed as the pin. Right there, velocity of shadow is at its max, and it's also equal to the velocity of the pin. The shadow and the pin are moving at the exact same speed right there at that point, and only at that point. So really, this equation and this equation are parallels to each other. They're exactly the same. They're not just parallels. So really, this has proven to us that the shadow is moving in simple harmonic motion.